This session on mathematical physics. My name is Simone Watzel from TU Munich, and I'm extremely happy to introduce Michael Loss from the Georgia Institute of Technology. Michael Loss received his PhD in 1982 from ETH Zurich. He's an eminent mathematical physicist with a lot of prizes. Among them, he's a fellow of the AMS and also a foreign corresponding member of the Chilean Academy of Science. He received the Humboldt Prize, and it is a great pleasure to introduce his talk. He will be speaking on the CATS model, variations on a theme.
Thank you, Simone. Let me first say that I would like to dedicate this talk to the memory of Maria C. Carvalho. She was a very good friend of mine, and we wrote together with her husband, Eric Carlin, many papers, and she passed away last year around that time. The work which I'm going to talk about, it's just an overview about things which we have done for years now, and this was with Eric Carlin, Maria Carvalho, and also Federico Bonetto, who is a colleague of mine at Georgia Tech. Okay, so the CATS model is a simple model, and I emphasize here the word simple. It's based on probabilistic assumption, and the idea is to understand certain aspects of the evolution of particle systems undergoing pairwise collisions. And in particular, one looks at this in a spatially homogeneous situation. So this is an enormous simplification, but that's in some sense the charm of this model. And so what one can study for that is of course, try to get a simple derivation of the spatially homogeneous Boltzmann equation and to formulate the problem of approach to equilibrium. And this was in some sense the aim of CATS when he cooked up this model. So here is a very simple one-dimensional model. So it's probabilistic for one-dimensional colliding particles. It's based on CATS from 1956. So the story is quite simple. You randomly pick, so it's spatially homogeneous. So the space we're looking at is only about velocities. Now you pick randomly and uniformly a pair. You pick randomly a scattering angle and with uniform probability. And then what you do is you take this pair Vi, Vj, these are the two velocities of the ith and jth particle, and you update these velocities by a rotation. So this is a very natural thing in the sense because it preserves kinetic energy. Now, what you have to do, of course, is you have to give them a certain time evolution. And the way you do this is you assume that these particles collide independently and they are associated with it an exponential random variable Tij with parameter lambda, which is this funny number here, which you can write as 2 over n minus 1. Now, the point about this is simply the following. It looks a little bit complicated, but what this is saying is that particle, in order to, the rate of collision of a single particle with all the others, is of the order 1. You can ignore the factor of 2. It's a 1 over n minus 1 here. That's reasonable, okay? So this is purely the probabilistic aspect of this model, but you can actually turn this into analysis. And the way you can do that is by writing down a master equation. And the master equation associated with this process is the following. You have a distribution, and remember, this distribution depends only really on the velocities, right? Which V1 to Vn, sorry. And what you have is, and of course on time, and then you have a generator for this semi-group, which is write down as Ln, which is n times the identity minus Qn, and Qn is this averaging operator. And you see here, it's quite simple. What you do is you look at the plane Ij in velocity space, and then you do a random rotation and you average over all rotation angles. Now, you might wonder why only kinetic energy is preserved. Why not also momentum? And the problem in one dimension is that when you have kinetic energy preserved and momentum, then the particles have only two choices. Either they go through each other, keep the velocities, or they exchange the velocities. Nothing else can go on. And this is not so interesting for our purposes. In particular, you might have a problem trying to understand the approach to equilibrium. This doesn't make any sense here, okay? So this is, in some sense, this operator. It's very simple, this Ln. It's, I should say, deceptively simple. And one can then ask various questions. So the first question, which Katz, I mean, here's a summary, right? The energy is conserved. When you have a symmetric distribution, we usually look at those where this function is symmetric in its variables. Then, of course, the time-evolved distribution is also symmetric. And another nice property is that this Ln, let me go back, this operator here is self-adjoint on the Hilbert space L2 of Sn minus 1 square root of n, okay? So look, E is the total energy, and it's reasonable to assume that the total energy, the energy per particle is of order 1. And that's the reason why we call this n, okay? By the way, the inner product, we will use this notation later on, is denoted by F comma G, as always, okay? So this is in some sense the whole model, right? And now comes the question, what can you do with it? And the first thing which Katz did was this notion of propagation of chaos. And in other words, his aim was to derive the Boltzmann equation, at least in the spatially homogeneous situation, from this simple probabilistic model. And so, as you can see, easily convince yourself is that if you start with a product of functions on the sphere, you see that the variables v1 up to vn are not independent. The sum of the squares must be n. So now you do not have independence really, and the evolution doesn't respect any independence. But what it maybe does, and that's the whole point, is it respects asymptotic independence. So this is what we now know as the notion of chaos. So what is it? You have a function f, which is given in L1, and you think of a sequence of functions fn, which depend on the variables v1 to vn. So in other words, this is a sequence where the functions acquire more and more and more variables, okay? Now we say that the sequence here is f chaotic if for any k in the natural numbers and any bounded continuous function from rk to r, this limit here, which I've written here, exists, okay? So you integrate over all variables over the sphere, you multiply by this phi, which depends only on k variables, and you take the limit as n goes to infinity. That should exist. And moreover, this limit should be the same for any bounded continuous function, namely a product of these f's. So this means essentially that asymptotically this fn is independent, okay? And there's a famous example, namely you take the function 1 on L1 as n minus 1 of square root of n. This is the radius, right? This is chaotic with respect to the Gaussian. This is an old result. It's French call it the Poincare sphere. The British call it Maxwell's theorem. Anyhow, it's a very simple calculation. It is highly recommended to do it at least once in your life. Okay, so this is chaos. That's what we call it. We call Fn a chaotic sequence with respect to f if this equation holds, this limit, okay? So now what can one say about that? So this is a theorem of Katz, namely it says the following. You start with a chaotic initial condition, which is F0 chaotic, okay? So F0 is any function in L1. You can easily construct such chaotic sequences. That's not very difficult. Then what he shows is that when you evolve this Fn0 with the full time evolution of Katz, the resulting function is still chaotic. And it has a moment, I mean, the first marginal, I should say, Ft. And this Ft is now a solution of the Katz-Boltzmann equation, which I've written down here. And what you notice is that this is an equation which is actually nonlinear. And the reason why it's nonlinear is that really what should show up here is the two-particle marginal. But of course, in the limit as n tends to infinity, this two-particle marginal actually factorizes and gives you this Boltzmann equation. Now, this is an interesting result because the way you solve the Boltzmann equation, you do the following. You start out with your initial condition. You construct a chaotic sequence Fn0. You get another. You look at the solution of the Katz equation of the master equation. That gives you again this marginal f of t, and you know that this marginal f of t is the solution of the Boltzmann equation. Of course, this doesn't tell you anything about uniqueness, but this is a nice result, and it gives you a very simple understanding how the Boltzmann equation arises out of a model. When you look at it, it's actually linear, right? When you look at this, this master equation. Okay, good. So then another issue is the approach to equilibrium. So if you start out with an initial condition F0, which is a probability distribution on the sphere, and you evolve it, and then it's very easy to see that as t goes to infinity, that this converges to the function 1 on the sphere. So this is what we would call approach to equilibrium. And how do you measure this approach to equilibrium in a sort of quantitative way? Well, one way of doing it is you look at the spectral gap. You see, this evolution, the Ln is a self-adjoint operator. So the e to the minus ln t is also a self-adjoint operator. And you can, therefore, the spectral gap using the spectral theorem tells you that the L2 norm minus, I mean, you take the f minus the limit as t goes to infinity, this L2 norm decays exponentially fast with delta n, okay? And delta n is the second eigenvalue. You see this, the first eigenvalue, the lowest, is 0. And then the next one is delta n. And you can also describe it in the way I've done it here, namely as the infimum of this typical expectation value over all functions which are normalized and perpendicular to 1. And Katz, in those days, in 1956, conjectured that this gap, delta n, should be bounded below by a universal constant c, strictly positive, independent of n. That's the whole point. And it took a while to prove this, and it was proved first by Elise Jean-Vresse in 1999 using Hongzhe Yao's martingale method. And then together with Eric Carl and Maria Carvalho, we managed to show that the gap actually was this number. It's actually very simple. And Maslan, I should mention, also computed many, many more properties about this evolution, okay? And you see clearly this is bounded below by 1/2. So this is a proof of Katz's conjecture, okay? So this is a very simple model. And the next question, of course, is can you make it more realistic? And one move is to go with hard sphere collisions. So we're talking now not anymore about a one-dimensional problem, but this time we're talking about really three-dimensional momentum and energy preserving collisions. So the space of velocities is now not anymore characterized only by the energy, but also by the total momentum p. And I've written here the average of the kinetic energy is E, and the average over the total momentum, the total momentum divided by n is p. So the way one should sort of visualize this is that the v, the velocity space, is in R3n. Then the energy gives you a sphere in R3n and 3n minus one dimensional sphere. And then what the momentum does is it cuts out with 3 more planes another sphere, okay? And this is kind of sort of crooked in this space R3n, okay? Now, this time, of course, since we're modeling hard sphere collisions, what you have to do is that the process is now different. This time, the parameter will now depend on the velocity difference. So again, you have an exponential random variable as before, Tij, that's the first collision time. And the parameter now is given by this funny object. Now, if Vi minus Vj, if this were not there, you end up with the original model, okay? So this leads to, now you have to sort of tell what the jump process is. Now, at the jump time t, the pair ij furnishing the minimum among all these Tijs, then the process jumps from V1 to Vn to a new collection of velocities. And these velocities, all the velocities V1, V2, and so on stay the same, except Vi and Vj change. And they change in this particular way. And you easily can check, obviously the momentum is preserved, and you can easily check that the kinetic energy is also preserved, provided, of course, you know that the sigma is a unit vector. And the question is, of course, how you choose the sigma. And the sigma is now chosen uniformly at time t, and the process then executes a collision step in which Vi star and Vj star are given by this expression, okay? This, by the way, models really hard sphere collisions. It's a kind of a strange parameterization. There are different parameterizations which are more in the physics literature, but this is very, very convenient for our purpose. Okay, so this is the process. And now you can, of course, write down a generator. And the generator looks like this. It's, again, the same as we had before, except you have now this Vi minus Vj in magnitude here. And what is the Fij in this parentheses here? That's just the integral of Frij sigma V d sigma. What is this Rij? It keeps all the velocities fixed for all k which are not equals I and j, and it changes and it takes this Vi star of sigma and Vj star of sigma, and you integrate this over sigma over S2. And by the way, I should say d sigma is, of course, a probability measure. All right? Good. So this is the generator. And this generator encodes everything. You can write down a master equation, everything what your heart desires. I should also say propagation of chaos is much, much more difficult. And this was achieved by Muhr and Mischler in 2011. And the reason why it's much more difficult is that, you see, the Vi minus Vj can be very, very large. This difference can be of order square root of n. Now, propagation of chaos means you make a statement about the limit as n goes to infinity. So you have to talk about unbounded things. And that makes the problem very, very difficult. By the way, I should also mention that Muhr and Mischler in 2011 proved many more things. They proved quantitative uniform in time propagation of chaos, but they used the Wasserstein distance. They also proved propagation of entropic chaos, where you take the relative entropy of Fn with respect to gamma, and I will explain these things later. You take the average, this will converge to the marginal with respect to gamma. I have to explain this later. And what they also provided are quantitative estimates on relaxation times, independent on the number of particles. So this is very, very beautiful work, but it's an approach which is different from what we take. Okay, good. So now let's go on and ask what happens with the gap. Now, the gap for three-dimensional momentum preserving collisions is a much more difficult problem, right? Again, you can see that 0 is a non-degenerate eigenvalue of Ln. The gap delta n, which depends on the energy Np, is of course by the first strictly positive eigenvalue of Ln. And it's a very simple computation which you can do, namely you can normalize this thing, namely you can relate the gap at energy E and P to the gap at energy 1 and 0, but you have this prefactor here. This is quite satisfying. And in 2020, Eric Carlin, Maria Carvalho, and myself, we managed to show that there is a strictly positive constant, which in some sense is explicitly computable, so that the gap is bounded below by this constant, okay, independent of n. And the point, of course, is I say explicitly computable, it's not a compactness argument. So there is a procedure, it's very, very complicated, and you can in principle, as I would say, compute this constant. Needless to say, this problem is much, much, much harder than the previous one-dimensional one, and it took us about, in total, about 50 pages. So this is difficult, but at least we know that now. Great. And now here's another point here. Namely, the gap is in general not a very good measure for the rate of approach to equilibrium. okay? And why is that? Well, you see, take any function in L1 intersected L2 and imagine that this function looks more or less like a product function. And then it's very easy to see that the L2 norm of that function grows like exponential in n, like c to the n, and c is a number strictly bigger than 1. So this is not really a good measure, right? Because when you have c to the n and you have to bring this down to some order 1 term over time, you need time of order n to do that, which of course can be the age of the universe, which is irrelevant for all practical purposes here. So what you would like to do is you would like to measure everything in terms of relative entropy. Now, relative entropy, I call it H. This is not really the entropy because I have the wrong sign, and this is the reason why I call it H. So H is positive. And H now will decrease to 0, right? That's sort of the idea. All right. So this is the definition, namely you integrate over the sphere. I'm back now again into this one-dimensional setting, f log f divided by g, and g is some reference state. And again, I integrate here over the surface measure over the sphere, which is, by the way, always normalized to 1. Now, the first thing you look at is, if you want to understand how this quantity decreases in time, then of course, the first thing you do is you choose the g to be 1, right? Because that's what you decay to. Because if f is the same as g, you get obviously 0. Then what you do is you differentiate the relative entropy with respect to time, and what you get is a negative expression. So you change the sign, and this expression is now non-negative, and you call it the dissipation. And in our case, when Ln is the generator, that's what the expression is. Now, the entropy production is defined to be the following. You take the dissipation and you divide by the entropy of the state, Fn, and then you take the infimum over all such functions, Fn. Obviously, when you start out with an F0 and you let it evolve along cuts, then you get h of f of t is less or equals e to the minus gamma nt times the original entropy. And of course, it would be lovely to see whether this gamma n depends on n, and how does it depend on n, and hopefully it doesn't depend on n. Unfortunately, this is bad news. It depends on n. So there was a theorem by Cédric Villani in 2003, where he proved for the one-dimensional Katz evolution that the entropy production is greater or equals 2 over n minus 1. Now you can say, well, maybe this is much too small, right? But it turns out there's a theorem by Amit Einaf in 2011, where he showed that for any epsilon, you can find a state f epsilon of n particles, such that the ratio of the dissipation and the entropy bounds gamma n, and this number here is less than a constant c epsilon divided by n to the 1 minus epsilon. So for all practical purposes, the entropy production goes like 1 over n. Now, of course, this doesn't really tell you that this here is the right behavior. You see, what could happen is that for a time of order 1, everything stays flat, right? Very flat. There's hardly any decay in time, and then suddenly it takes over and you have a nice exponential decay with a nice rate. So this is completely unknown whether this happens or not, but I personally think it cannot, and it's illuminating to understand a little bit how this result of Einaf comes to be. Namely, what he does is he takes a state where he packs almost all the energy in the small part of the particles. So it's a large set of particles which doesn't have any energy. And what now happens is that these particles which have all the energy have to impart all the energy into the others and eventually drive this thing to an equilibrium. And that takes an enormous amount of time. And I think this is presumably the right picture. So in other words, when we have extreme initial conditions, even in realistic circumstances, I would imagine we would have to wait a long, long time before we reach equilibrium. Okay. So therefore, talking with Federico Bonetto, we came up with a different tack on this problem. Namely, we look at systems interacting with a finite reservoir. So approach to equilibrium we envision in the following way. We have a large system which is in equilibrium. We attach to it a small system, and which is not in equilibrium. And then we look at the entropy of this small system and see what happens. And the way we do it is we take a master equation of the following type. So here's the generator for the system. The system just runs by itself, just like a Katz model. Then you have the system of the reservoir. Again, this is like a Katz model. So at the moment, these two things don't interact. But what you do now is you let them interact in this fashion. So you let the particles of the system and the particles in the reservoir collide with each other. And the way you set this up is you want to make sure that the collision rate is of the order 1. Here it's going to be mu. You notice when you take a particle of the system, well, it has n particles in the reservoir to collide. And so you average this with a 1 over n, so the collision rate is mu of that particle. Okay? So now, of course, the evolution is on functions which depend on the velocities in the system, but also in the velocities in the reservoir. Okay, and for simplicity, we take now functions in L1, not anymore on the sphere. That's too complicated in a way. All right, so this is our system, our evolution. Now, initial conditions. What do we say? Well, the reservoir should be initially in equilibrium. All right, so this is the equilibrium is described as a Gaussian. And I apologize, but I just put here a pi. You see, you can choose the temperature in any way you like. That's just a constant. And what we do is we take a normalized Gaussian with temperature 1 over 2 pi. It's just easier to write. Okay, so we take now the Gaussian. This is the reservoir at time 0. This is the F0 of V. And that's the system. And now we let this whole story run by the time evolution. And what we do is we integrate over all variables of the reservoir, because that is not very interesting, right? We don't care about the reservoir, really. So that delivers us a function which depends only on the velocities in the system. And now we look at the entropy of this F with respect to the Gaussian e to the minus pi v squared. Okay, that's this gadget here, all right? Good. Now, what you would expect, of course, is if you stick in this f of vt into this expression, that would decay. And indeed, it does. Namely, how does it decay? You assume that the initial condition has an entropy, which is finite. That's this expression here. Then you can say that after time t, the h of f of t is less or equals this quantity here, times h of f0. Now, what is this quantity? Here we have m divided by n plus m. Here is n over n plus m. So this is a convex combination. And here you have an exponential. And you notice, by the way, that when n is very, very large, this converges to mu divided by 2. So this is a fixed rate. Okay? So in other words, we can say that through the interaction term, despite the fact that correlations will build up over time in the reservoir, the entropy will decay. The reservoir will be out of equilibrium after finite time, but somehow it's not so bad. It can still manage. And if n is very, very much larger than m, the entropy of the system decays to a small value at an exponential rate of order 1, right? So this is tiny here. Remember, n is much, much larger than m. This is almost 1, and you go to with an exponential rate towards this tiny number, okay? Now you might wonder, can it be that this number should actually be 0? Well, the answer is no. Why? Because the Gaussian e to the minus pi v squared, this guy, is not the equilibrium state. You can easily check that. It's not in general, okay? All right. So this is the situation. One can also show, by the way, that the information, that's this gadget here, right? Where you take the gradient of f squared divided by f, you integrate it against the Gaussian. This information has exactly the same decay. This was a result by Federico Bonetto, Han Rui, and myself. And it's interesting, by the way, the proof is very, very easy. And moreover, this fact also implies this fact here, which we proved. This was very difficult to prove. We used all sorts of things like Braskamp-Lieb inequalities, etc. But using the information, this result follows much, much easier. Okay? So this is in some sense a satisfactory result. Yes, the entropy doesn't decay to zero, but what it does is it becomes very, very small. Okay? Great. So let me now go to another theme about the Katz model, namely to quantum master equations. You see, we can actually draw up a similar scheme for quantum systems as we did for the Katz system. So now you start, of course, with a single particle Hilbert space. That's for a single particle. We assume it to be finite dimensional. And you also need to specify an energy for the single particle, which we give as a single particle Hamiltonian, which is a self-adjoint operator on this Hilbert space. And we assume that it has eigenvalues E1 to ED and eigenvectors phi1 to phi d. Okay? So then your n particle Hilbert space is sort of the configuration space. I should say it's the velocity, it corresponds to the velocity space, which is in our case L2. All right. And the Hn, this is your Hamiltonian, your multiparticle Hamiltonian, that corresponds to the energy as we had before, namely the sum of the Vj squared. Okay. Vj squared, by the way, is the energy of a single particle, which has its correspondence in H. Okay. So then you ask yourself, well, how can you cook up an evolution on this problem? So what you need is you have to specify something which you call binary collisions. So you take a Q, which what does it do? It takes operators on the two-particle space to operators on the two-particle space. Now, why do I talk about operators? Because the way you describe systems in quantum mechanics, you describe them through density matrices. So this is the density matrix is a positive operator now on H2, and its trace is 1. And what the Q should do, it should map density matrices to density matrices. We would like it to preserve the energy on this, and it should be completely positive. That's a desire. This is desired because that makes it a viable quantum evolution. And we would like it to be self-adjoint. That's very helpful in order to do analysis. And self-adjoint here means the following. You have the inner product given by this trace, and the Q of A comma B should be the same as A comma QB. So you essentially are pushed towards writing down a collision operator in the following way. Namely, as an integral over some measure space C with some probability measure d mu sigma, and these u sigmas are unitaries, and A is any operator on the Hilbert space H2. So what are the desideratas about this C and the U? Namely, the U should be the set of unitary operators in H tensor H. Now, that the energy is preserved, it means it should commute with the Hamiltonian of two particles. That's the first thing. Now, in order to have it self-adjoint, what you need is that the set of U's, sigma in C, and U star, sigma in C, should be the same set. And the map, which maps sigma to sigma prime, which maintains this relation here, should be measurable and should leave nu invariant. Once imposed this, you see right away that this form is self-adjoint. That's easy. Now, there is another little thing one has to worry about, namely the following. When you have two particles colliding, it looks like a symmetric thing. So when particle 1 collides with particle 2, they should be the same as particle 2 colliding with particle 1. So what you need is a swap operation, which just exchanges the factors in the tensor product. And what you need again is that this U of sigma, sigma in C, and this set of operators is the same. And the map sigma to sigma prime should be again measurable and leave nu invariant. Okay? So you can do that. So let me give you yeah, maybe I should also say what is an ergodic collision specification. You see, it's very easy to see that so the algebra generated by the spectral projections of H2, okay? What is that? This is essentially the algebra of all continuous functions of H2. And you can easily check that this algebra commutes with use of sigma. In other words, it's in the commutant of u sigma for all sigmas. Now, of course, in general, the commutant is bigger. But what we require now is to make this collision specification ergodic, we require that this commutant is equals to the algebra generated by the spectral projection of H2. Okay? So in other words, these operators have to be sufficiently rich in order to have a reasonably well-defined gadget which you can do analysis with. Okay? So since this is very complicated, I give an example. Let's take H to be C2. Then Hn is the n-fold tensor product. And the Hamiltonian, we take the simplest you can possibly imagine, has eigenvalues 0 and 1. Then you have this Hamiltonian Hn, has eigenvalues 0 up to n, with certain multiplicities, of course. Here is the H2, I've written it down. That's this tensor, this guy tensor 1 with one tensor this guy. And this gives you this matrix. The eigenvalues obviously are 0, 1, 2, and you see 0 is single, 2 is also single eigenvalue, and 1 is a double eigenvalue. And the eigenprojections are just the ones which I've listed here. It's completely obvious, okay? Great. Good, and then you have to do the unitaries, and what we're going to choose is, we're going to choose our C to be the fourfold product of the one-dimensional sphere. The sigma we describe in this fashion here, e to the I phi, e to the I theta, e to the I psi, e to the I eta. And then the u sigmas we choosing to be this way. Okay, and you see this is in some sense here is a general unitary 2 by 2, and here you just have phase factors. They are independent though. Okay, and for nu you choose the uniform probability measure on C on this space of fourfold product of the sphere. Okay, so that gives you a collision specification. Well, is it ergodic? Well, it's a simple computation which you can do. You take the Q of A and you compute. And when you do that, you stick in an arbitrary operator 4 by 4 matrix in here, you get a diagonal. And what you easily see is this is precisely A11 P0, A22 plus A33 over 2 P1, and plus A44 P2. So that's in A2, the algebra of spectral projections. And therefore, you can say that U of sigma, sigma prime, the commutant, well, what is it? It's certainly all the guys A, which are left invariant by Q of A, that's equals A2, and therefore this collision specification is ergodic. So that's very easy. Very good. So now you can cook up a quantum Katz operator. And how you do that? Well, we have defined the Qs, right? Here, the Qijs. And now what you do is you choose the Qijs to be the guys which we have defined before, like here, except that the Uijs act non-trivially only on the factors I and j together, right? So so you have to imagine you have an n-fold tensor product. You have all factors except the factor I and j, all the factors otherwise it acts as the identity, but on I and j, it acts in a non-trivial way described as we did before, okay? So that gives you a Qij of A, and now A is an element of the bounded operators on Hn. And here's the Qn, which is the sum, okay? You see, it's exactly the same as we did with Katz, except now it's in a quantum mechanical setting. And you can actually prove a few things. The Qijs, of course, preserve positivity, they preserve the trace, and of course, the Qij of the identity is the identity. And this is known as a quantum Markov operator. And restricted to density matrices, this is also known in the quantum information community as a quantum operation. And now you can write down again with our Ln a quantum master equation on density matrices. Rho is a density matrix. Here it is written. And of course, it generates a completely positive trace preserving semigroup. That's very easy to see. And you can solve it simply by exponentiating the ln. Remember, the ln is just a linear operator on the space of bounded operators on Hn. So it's very easy in principle. Of course, if you want to understand a little bit more in detail what this thing is doing, that's much more difficult, right? So for example, is there propagation of chaos? And what is then a quantum Katz-Boltzmann equation? So how would you define this? Well, the first thing you would have to know is what is a symmetric density matrix? Yes, the rho n is symmetric when you can swap factors and you don't change the rho n. And then you define the one particle marginal. You take the trace of all factors except the first, and you assume, I forgot to put an n here, that this limit exists, and it's a single particle density matrix. And likewise, when you take the trace from k plus 1 to all the way to n, you should get the tensor product of these density matrices. And then, as before, you can show that this time evolution P and T, which is the time evolution given by this evolution equation, turns out to be it propagates chaos. Okay, I've written this down here. But let me just point out what is more interesting. What does this rho of T do? Well, it turns out the rho of T satisfies a nonlinear Katz-Boltzmann equation. I've written it down here, where here A star B is what you call a quantum wild convolution. It's given by this gadget here. Okay. Now I understand this is a little bit fast, but I don't really have too much time anymore to explain all these things. Some of these things will be actually written down in the proceedings. Okay. So this works out quite nicely. It's the proof is a little bit tricky, but it's actually quite natural. Now, let me also point out a new concept which occurred to us recently, namely the adjacency graph. You see, think about the following. Suppose you start out with a psi alpha, which is a state in your n-particle Hilbert space. And then you can cook up this density matrix, psi alpha. And after one collision, what do you get? Well, you get that this, after the collision, you get that this new density matrix consists of eigenstates, that's a linear combinations of the form psi gamma, where only two indices got changed, right? All the indices are the same as say alpha L are the same in psi gamma are the same as alpha L, except for L equals I and J, things got exchanged. Okay. I'll put it differently. What has been done is in this process, two indices got exchanged. And so when we have alpha equals beta L and alpha I equals beta J and beta I equals alpha J, then of course the alpha and beta differ by a pair transposition. This graph is we call the adjacency graph. And the edge set of this graph we call EN. So adjacency means any two indices that differ by pair transposition are adjacent. And remember, the indices are n tuples in this space. Each alpha I takes values from 1 to d. Okay. Here's an example. In our example where we had the Hamiltonian 0, 1, it turns out that this graph is a regular graph. The number of edges are given here, the number of vertices are given here, and even the valency of the vertices are known. And by the way, it depends only on the number of zeros. You remember the alpha consists now of zeros and ones, right? These are the only energies which we have. And it depends only on the number of zeros. And the number of zeros plus the number of ones have to add up to n. Okay, so this is an example. What turns out, what is interesting is that if you want to understand the equilibrium states are given as the projections of the density matrices onto the commutant of all these operators here. And it turns out that these equilibrium states are in one-to-one correspondence with the connected components of this graph Gn. And you can write them in the following way. Pj, this project, is given in this fashion, where the alpha, these indices, these multi-indices, are in the connected components of this graph. Okay. Now, one final thing here. I should say, one can do many, many things. In particular, one can, for example, prove that in certain cases, for example, when the eigenvalues of the Hamiltonian are rationally independent, then this the commutant is actually equals to the algebra of the spectral projections of the Hamiltonian Hn. This is one thing which you can do. You can also prove a few other things about Lindblad evolutions, which I don't have time to do anymore. But in any case, I thank you for your attention. And this is the end. Thank you.
Thank you very much, Michael. Unfortunately, there's no time for a Q&A session, but Michael Loss is very happy to answer any questions if you contact him by email.
Thank you.